Hey, welcome back. Maybe for the last time for this particular worksheet. So this is the ballistic trajectory. I've reconfigured a little bit because what I wanted to do was to undo that limitation of the drag force being constant over the flight of the projectile. And in doing that and setting it all up, I decided to reconfigure it. It's starting to get reasonably complex. So to configure it a little bit more like I normally do with more complicated worksheets. So here we're in it. I'm going to walk you through a little bit of the changes that I've done, how I've reorganized it and restructured it, and you'll see some of the reordering is to facilitate that calculation to allow for an instantaneous velocity update and thus an instantaneous force update in the drag. So everything else is pretty much the same. So I've collapsed or made it slightly more condensed here. So we have our initial conditions. I've moved up our projectile definition so we get the entire problem definition up front. And then we go down and I break it up into the X and Y components of the initial velocity. And that's really no change, maybe a little bit of order difference, but that's about it. Now this is a format that I rather like when I'm going through complex calculations. And what that is I use the collapsible areas or regions. And so I give the title of what I'm going to do, consider the location to determine gravitational constant and atmospheric density. And then underneath that, I give the outputs, right? I don't need to see the calculation. If I want to see the calculation, I can open it up and see the calculation. So here I've popped it open. You'll recognize this from the previous video. I have my list box where we can choose the location. We have our checkbox where we can decide either drag or no drag. And you'll see it updates the atmospheric density or it makes it equal to 0 if you do not wish to consider drag. So that, again, no change. This is simply just making it all look a little tidier and getting it in the right order for the structure. So now we get into a little bit of the changes to the calculations. So the first one is, it would be easier for me if I knew how long the flight was going to be, and then I could break the time array into an equal number of segments. And so the easiest thing to do is, because we're assuming that the drag is only acting in the horizontal direction, which is reasonable for most conditions. So I was able to basically use my equation for position in the y direction, my initial position and velocities, and just using the gravitational constant, the one coming from the location box, and with that put it into my solve block. You've seen the solve block before, and again it just comes out with the time of flight. So really the only thing different here is that I previously had this for both the X and the Y, but now I'm just using it for the Y direction to determine what the overall duration of the flight is going to be for it to come back to 0. And so we get our T sub F is equal to 3.091 seconds. So this is where the hard part is to break it up into a piecewise calculation. So we're going to use range variables and arrays to basically do a piecewise calculation as we go through. So the first part here is to do the calculation itself. So use a piecewise calculation to determine the position in the X as horizontal acceleration changes. And you'll see right parallel to that, I also create another array for the Y direction, just so that I have the matching arrays for graphing purposes later on. So just for fun, I remember we had played with our slider. Version 11, we've got our labels in here, so we're able to do this. And this is basically saying, how many steps do you want in your calculation? Now this gets really interesting, and we'll come back to it at the end. Depending on how many steps you choose, of course, because it's a numeric calculation, that's going to allow you to converge as you increase the number of steps towards the actual solution. And quite frankly, depending on what the choices are, if you don't have it high enough, you could go down to a number low enough whereby you actually get a really erroneous answer. And I'll show you that when we get there. So I've got it set to 30. That's going to be fine for most of our conditions. And then I can just figure out what my time step is, my delta t. So I take my total time of flight divided by the number of steps, and I get a time step. I'm going to roll this up to the top so we can see more coming in. So we're going to create a range variable. I'm going to use j just because when I was building this, I had already used I further down, building it out. So I'm going to use j. I set j equal to 0, steps by 1 up to n, to the number of steps. So now I just wanted to try this out. It's a new function, if you will, within version 11. So you can test to see if you're not sure if your variable is a range variable or if it's an array. So we see here, I've tested it, is range j, and we get a value back for 1, which is indicating it's true. So it is a range variable. Should know that from the way we set it up, but wanted to try that out. Then on the next step, we have use the range variable, so j, to create a time step array of j steps, each of delta t. And so in this case, we have t, and just this is the t with the square bracket, left square bracket to get to it. So I'll show you if we're doing it here. It is the left square bracket to get down. And so it is saying for the jth element of the tth array, okay, and that's what it is. And it sets it equal to j, which is a range variable, multiplied by delta t. So it's going to go through and multiply it by delta t for every value in the j range variable. That gives us our array for t. So if you wanted to test, we're kind of running out of space here, but if I wanted to say t is equal to, and you can see all of the values in the array there, and that's what it's arrived at. But we don't need to see that. We can get rid of that. And just a reminder, at step 0, so this was the calculation for the drag force, okay, and it's using the initial velocity. So at time 0, for our force is going to be in the x direction, is going to be equal to the drag force using the velocity at time 0. So that gets us started. So that's an initial condition, if you will, for our drag. And it comes out in newtons. Now here, we're going to ignore the one to the right. So that's basically doing the y component. It has a constant acceleration, a few other minor details. But if we look to see what's going on the left, this is where we get our adjusting our drag force based on the instantaneous velocity. So what are we doing here? So you'll see it's basically using a program. We set for the initial condition, we set I equals 0, and we come up with our initial conditions, right? Time is 0 seconds. Our x at I equals 0 is 0 meters. Our velocity, x prime being velocity at 0 is equal to our initial velocity in the x direction. And then we have our acceleration at time 0 is equal to our initial force, which we just calculated up here, divided by mass, and that will give us our acceleration for that first time step. And then we go into a bit of a loop, and it's just for the remainder from I equals 1 through to n plus 1, and we're just going to update it in a piecewise calculation. So I did do a little bit of a, so just so we can see it picture-wise, I did create this. So this is what we just talked about here. And now for every step, we're going to update so that the new t at I is going to be I times delta t, which is good. Then we have our position, and we use our position calculation using the position, velocity, and acceleration from the previous time step. And then we update our velocity based on the velocity of the previous time step plus the acceleration of the previous time step times delta t. And now that we have an updated velocity, we can update our acceleration using the same equation as we did the last time, only in this case we're not using the initial velocity, we're using the velocity from the previous time step. So it's a numeric process. The greater the number of time steps you have, the minor errors within each time step tend to disappear, and we should be able to converge to a reasonable solution. And we just repeat that. And so that's what this code does here, is it basically does what I just described in that image. And returning a value for x each time it goes through the loop. And so that should return an array for x of positions at the different time steps. I've repeated it for y with those ever so slight differences like the constant acceleration, and that comes up with our positions in y. And that's our calculation. So if I collapse that, okay, and now we can look at our results. So here we go, we have it graphed. In this case, we're graphing the two arrays against each other, x in meters, y in meters, and it's going to graph a single data point for each time step in the array. And I put this down just to calculate the distance, so I'm just doing the maximum at x, and so that's the distance at which it comes back to 0. So we're getting 19.049 or 19.05 meters. And then the rest of this is pretty much as we saw it before, where we can do our tolerances and everything. The only thing I did is I added an absolute value sign around here, so it didn't matter if we missed being too short or too far away, we'd still get the same behavior. So I did add that absolute value sign. So does it matter? Well, if I were to look at this calculation using a constant velocity, which we already know because we did that on our previous sheet. So here's the previous sheet. This is the same calculation done up. And we're getting a value of 18.82 meters compared to a value of 19.049 meters, which is roughly 0.2 meters on 20, right? So that's about a 1% error. So it's really up to you to decide whether that is a significant error given the nature of the calculation you're doing. But here we're seeing a much more accurate calculation. Now, where it's really going to make a difference is when we go up, if we choose Venus. And if we consider drag, we'll see a really interesting curve. It's only going out about 4.5 meters for the same initial conditions as the Earth calculation. But if we turn the drag off, it goes out there. Now, what does that calculation, so, it was about 5 meters. What does it do if we don't consider or we have constant drag? So let's go here in this calculation. We have Venus. We're considering drag, right? So it's going to be a constant drag, which is because the atmosphere is so thick. That's a really considerable amount of force. And so we didn't really look at it too closely. But this is actually showing it as going backwards, right? It leaves on a positive trajectory. But because the acceleration is so strong right out of the gun, if it were to stay constant, which it won't, it would actually, before it could come back to Earth, would turn it around and have it going backwards, and it would go the wrong direction. So this is a completely erroneous calculation based on the assumptions. The assumptions do not allow for a reasonable calculation. But we can get that reasonable calculation now that we have this piecewise calculation update. Okay, so we're now in Venus. We're going to consider drag, and we're still getting a positive number, and it's going out at around 4.6 meters. Now, I did talk a little bit about in your calculations, if we change our n down to something small, even here, we're going to get a result which is starting to struggle, right? It really is starting to struggle because it's not refined enough to get it. And if we drop down even lower, you can see we'll have near the same problem that we had before because it's not precise enough. It has too large a time step at an arbitrarily elevated velocity. And we can, if we go down, bring that down to about 5, 6 or 5, and you see the same sort of thing, right? It's coming back down. So you do have to make sure that you've got an adequate number of time steps if you want to have a reasonable calculation if you're using a really thick atmosphere. Doesn't make as much difference on the Earth calculation because it's not as severe. So that's it. That's all I wanted to do. Like I say, you can see how we have this nicely set up so we can fit it all on one page from question all the way to the end, laid out the way it is. And we only have to do a dive into each section if we're going to update something or want to look at something. But say if you were just looking at different projectiles, you don't have to see all the rest of those calculations. You can just do it in here. The other place to be careful here, I haven't put any flags or warnings, is if your time isn't correct, you could go down to a negative root, and you want to make sure that you have the positive root that it's converging on. So other than that, I think it's pretty much done. I think we've figured it out. So this was all about those calculations, using the programming to do a piecewise calculation so that we can get an update and saving the values into an array which we could then graph. So if that was useful to you, that makes me happy. And I'm not exactly sure what I'm going to do next, but I'll come up with something and hopefully we'll see you then. Cheers.